Hello and welcome. Today we are going to dive into one of the biggest, most mind-bending challenges in all of science, quantum error correction. You see, it's the one thing that could finally unlock a true computing revolution. But to get there, we basically have to outsmart a fundamental law of the universe itself. Just think about the possibilities for a second. We're talking about quantum computers that could simulate molecules with perfect accuracy, letting us design brand new, life-saving drugs, not in decades, but in a fraction of the time it takes today. And it doesn't stop with medicine. These machines could help us discover things like new superconductors for perfectly efficient energy, or create revolutionary batteries, or maybe even design materials that are stronger and lighter than anything we can imagine. The potential is, well, it's totally transformative. But, and this is a huge but, there is a massive problem. For all their incredible power on paper, the quantum computers we can actually build right now, they make mistakes all the time. And these errors are pretty much the single biggest wall standing between us and that amazing future. And the scale of this problem is, well, it's just staggering. For a quantum computer to be a truly useful, world-changing tool, its error rate has to get better by a factor of about 10 billion. Yeah, you heard that right. Not 10%, not even 10,000 times better. 10 billion. That is the enormous gap we have to close. So let's take a closer look at this so-called quantum glitch and really get to the bottom of why it's such a massive headache. Here's a good way to picture it. Imagine you're doing a really long calculation on a calculator, something with millions of steps. But what you don't know is that the calculator is randomly going back and changing the numbers you already put in. By the time you get to the end, your answer would be complete nonsense, right? Just gibberish. Well, that's exactly the kind of situation quantum computers are in every single moment they're running. So why? Why are quantum computers so incredibly fragile? To get that, we need to understand the whole universe of errors that these quantum systems are constantly battling against. The main culprit has a fancy name, decoherence. A quantum bit, a qubit, exists in this really delicate, fragile state. But pretty much anything, a stray vibration, a tiny change in temperature, any little bit of electromagnetic noise from the outside world can mess up that delicate balance. And when that happens, the information just leaks away and gets lost forever. And this decoherence shows up in a whole bunch of nasty ways. You've got your bit flips, which are kind of like a normal computer error, but then you have phase flips, which is a purely quantum kind of error that messes with the qubit's wave-like properties. Then there's crosstalk, where qubits start accidentally messing with their neighbors, and even leakage, where a qubit literally escapes the system it's supposed to be in. It's a mess, a truly chaotic environment. Now, you might be thinking, okay, that's a lot of errors, so why not just make a backup copy of the data, like we do with everything else? Well, this is where the story gets really interesting, because we slam right into a fundamental, unbreakable law of physics. And this really gets to the heart of the challenge. With our everyday classical computers, redundancy is everything. We make copies, it is our #1 defense against errors. But in the quantum world, that exact strategy is completely forbidden by something called the no-cloning theorem. The rule is simple. It is physically impossible. This isn't some engineering problem that we might solve one day with better tech. No, this is a fundamental rule of how the universe works. The very act of trying to measure a quantum state to copy it automatically messes it up and destroys the original. So our best weapon for fighting errors is just gone, off the table. So, if you can't copy the information, how on earth are you supposed to protect it? This is where scientists came up with one of the most brilliant, most elegant insights in all of modern physics. They found a clever workaround. The solution is just beautiful. The big idea was, instead of making a copy, you take your single piece of important logical information and you spread it out across many physical qubits using entanglement. This links them all together, so they share a single collective fate. The information isn't really in any one qubit anymore. It's encoded in the pattern of relationships between all of them. This insight leads us to a really clear 4-step process, a correction pipeline, if you will. First, you encode the information across all those physical qubits. Then comes the really clever part, syndrome measurement, where you check for errors. After that, a regular classical computer decodes that information to figure out exactly what went wrong. And finally, it applies a recovery operation to fix the mistake. And that second step, syndrome measurement, is where the real magic is. I mean, how do you check for an error without looking at the data, which would destroy it? You do it indirectly. You ask questions about the relationships between the qubits. It's like checking if two jigsaw puzzle pieces fit together perfectly. You can tell if a piece is in the wrong place just by how it connects to its neighbors, right? You never actually have to look at the picture on the pieces. It's called syndrome measurement because just like a doctor diagnoses an illness from a set of symptoms, the computer diagnoses the error from a pattern of clues, the syndrome, without ever seeing the precious data itself. So we have this incredible, powerful theory. But how do we actually translate that into a real blueprint for a reliable quantum machine? Well, let's explore that path to perfection. So researchers have come up with a lot of different codes, which are just strategies for spreading out the information. The early ones, like the Shorenstein codes, were absolutely groundbreaking. But as you can see, they were pretty demanding. They needed a high qubit overhead, meaning lots of physical qubits for each logical one. And they also needed complicated long-range connections between them, which are super hard to build. The real story here is that trend you see in the last column, the slow and steady march towards practicality. And that brings us to the current frontrunner, the surface code. Its biggest advantage is just pure real-world engineering. It arranges all the qubits on a simple 2D grid, and, this is the key, it only requires each qubit to talk to its immediate neighbors. That's a design that we are actually really good at building with modern chip technology, which makes it, by far, the most promising way forward. And, all of this hard work is supported by this profound, beautiful message of hope called the threshold theorem. It is essentially a mathematical guarantee. It proves that this problem that seems so impossible is in fact solvable. What it says is this: as long as the error rate of your individual physical parts is below a certain tipping point, a threshold, then you can keep stacking up these error correction tricks to make your final calculation as perfect as you need it to be, no matter how long or complex it is. This is the theorem that gives everyone in the field the confidence to keep pushing forward. So, there you have it. We've gone from what looked like an insurmountable problem, smashed into an impossible law of physics, and came out the other side with an elegant workaround and a practical blueprint. The theory is there, the path forward is becoming clear, and the experimental hardware is just now, finally, starting to cross that critical threshold. The question really isn't if we can do it anymore. The real question is, can we now take this blueprint and build the world-changing machine we've been dreaming about?